You've probably never thought about this, but stand close enough to a freight locomotive in the rain and you will. There's a person sitting behind that glass, doing 60 miles per hour, staring at the same track for hours. The windshield is massive. The cab is shaking. Rain is hitting that glass at full force, and at some point your brain starts asking questions you can't answer. Does the engineer even have wipers? If they do, why do they look nothing like anything on a car? And if trains have all that technology, why does the whole system look so old? The answer is messier and more interesting than you'd expect. Trains do have windshield wipers. Every freight locomotive in service in the United States is legally required to have them. Every passenger cab, every commuter rail unit. It is a federal requirement, enforced by the Federal Railroad Administration. No wipers, no revenue service. Full stop. But here is where the premise of the question becomes interesting. The moment you actually stand next to a locomotive cab and look at what is on the windshield, you realize you are not looking at anything like what is on your car. The comparison breaks down fast, and the reason it breaks down tells you a lot about how rail engineering actually works, which is to say, nothing gets designed the way you would intuitively expect it to be. A car wiper is driven by a small electric motor tucked under the hood. It draws about 3 to 5 amps of current when running, roughly the same power draw as a desk lamp. It pivots from a fixed point at the bottom of the glass, sweeps a curved arc, and the whole system weighs maybe a few pounds. A freight locomotive wiper is driven by compressed air, the same high-pressure reservoir that powers the train's braking system. That reservoir runs at around 130 to 140 psi. To put that in physical terms, a standard car tire runs at about 35 psi. The locomotive's air system runs at 4 times that pressure, and it exists primarily to stop hundreds of tons of steel moving at highway speeds. The wiper taps into that same supply. The wiper motor is a pneumatic vane motor, a small housing where compressed air pushes against angled blades to generate rotation, and that rotation drives the wiper arm back and forth across the glass. That's not a quirky detail. That choice, AIR over electricity, is a deliberate engineering decision, and it comes from a specific problem. A diesel locomotive already has compressed air running everywhere. The main brake pipe, the sanders that drop grit on the rails for traction, the horn, the door controls. The whole machine is built around a central air supply. Adding the wiper to that system costs almost nothing in terms of new infrastructure, because the pipes and valves are already there. Running an electric wiper system on a locomotive is a different story. You would need a motor mounted on the exterior of the cab, wiring routed through the cab wall and sealed against moisture, and that motor would need to survive the kind of sustained vibration that shakes the bolts loose on equipment that is not specifically designed for it. A diesel locomotive runs on an engine that, in the case of the EMD SD70, produces around 4,300 horsepower from a 16-cylinder prime mover. The whole cab shakes with a low frequency that automotive components are simply not built to handle for thousands of hours of continuous service. Pneumatic motors are tougher. They have fewer precision parts. When something fails, it fails simply, often in a way a mechanic can fix without specialized tools. The reliability curve on pneumatic systems in heavy industrial environments is well established. Railroads have known this for over a century, which is why air runs so much of what a locomotive does. But the air supply is only one part of why the systems look different. The bigger issue is the glass itself. A car windshield is designed around aerodynamics. The glass is raked back at an angle, typically between 25 and 40 degrees from vertical depending on the vehicle. That rake does something important. At highway speeds, airflow runs along the surface of the glass and helps carry water off. The wiper still has to work, but it is working with the air rather than against it. The glass is also relatively small, maybe 54 to 62 inches wide on a standard car or pickup, and it is a single piece of roughly uniform curvature. A locomotive cab windshield is nearly vertical. The cab face is a blunt wall, because a locomotive is not trying to be aerodynamic in the same way a car is. At 60 miles per hour, rain hits that glass almost straight on. It does not sheet off. It hits, spreads, and the wiper has to move all of it mechanically, with no help from airflow. The swept area is also larger. A typical freight locomotive cab has two side-by-side panes, each needing its own wiper, and each pane can span 30 or more inches. The glass is often heavily curved to match the cab profile. That curvature creates a specific mechanical problem. A wiper blade moving across a curved surface has to maintain consistent downward pressure along its entire length, from tip to pivot, or the blade lifts off in the middle and leaves a wide streak right across the center of the driver's sightline. Getting that pressure distribution right requires the blade geometry to be custom matched to the specific curve of each cab design. You cannot take a blade off a different locomotive and expect it to work. It is not like swapping wiper blades on a Honda. Then there is the force required. At speed, the aerodynamic drag pushing back against the wiper arm as it sweeps across the blunt face of the cab is significant. Too little spring tension in the arm, and the blade lifts off the glass. Too much, and the blade drags, chatters, wears out fast, and creates smearing that is worse than just leaving the water there. Calibrating that tension correctly for the specific windshield geometry, cab speed range, and wiper arc takes real engineering time. Many locomotive wiper systems also include a pressurized washer fluid circuit, again fed by the pneumatic system, that pre-wets the glass before the blade moves across. On a car, you press a button and the fluid sprays. On a locomotive, the whole fluid delivery system runs on compressed air, including the pump. In 2017, Transport for London was preparing to introduce a new fleet of trains for the Elizabeth Line, a major cross-city rail corridor. The trains were the Class 345, built by Bombardier. Before entering service, they were sent to Vienna for winter testing. Snow, ice, sub-zero temperatures. The wipers passed everything. Back in London that summer, during warm weather operational testing, the wipers failed. Not from rain, from insects. Bug impacts had accumulated on the windshield, and the blades could not clear them. The software controlling the wipers was calibrated for the pressure needed to move water across glass, which is relatively low. Insect residue behaves completely differently. It is adhesive, it dries quickly, and dragging a rubber blade across it without sufficient force just smears it into a translucent film across the driver's primary sightline. The fix was a software change. The wiper control system was reprogrammed to apply variable force depending on whether the glass surface was wet or dry. A wet screen needs lighter pressure. A dry screen with debris stuck to it needs significantly more, enough force to shear the material off rather than just pushing it around. The engineers adjusted the force profile and the system worked. But the fact that an otherwise well-tested fleet of trains shipped without anyone having tested the wipers against insects tells you something about how complicated these systems actually are in practice. You test for what you think of. You find out what you missed when the train goes into service. Train wiper systems don't get serviced the way car wipers do. A car sits in a garage, gets inspected, gets new blades when they streak. A locomotive might run continuously for days across multiple states before it returns to a maintenance facility. Whatever the wiper system encounters, rain, sleet, insects, mud kicked up from the track, ballast dust, it has to handle them reliably, without any intervention. That requirement for long-interval reliability is what drives every design decision, from the pneumatic power source down to the blade compound. The wiper as a concept is being questioned at the high end of rail technology, and the argument starts at speed. A conventional pivoting wiper arm has an upper speed limit. On road vehicles, aerodynamic lift typically makes wipers unreliable above about 100 miles per hour. A standard highway car rarely exceeds 80 miles per hour, so this never becomes a real problem. But high-speed rail operates in a different range entirely. A Japanese Shinkansen runs revenue service at around 200 miles per hour. At those speeds, a conventional wiper arm would be fighting aerodynamic forces it cannot overcome. Some high-speed rail systems use hydrophobic glass coatings instead. The coating makes water bead into tight droplets that roll off under aerodynamic pressure above a certain speed threshold. It is the same category of technology as consumer products like Rain-X, but engineered to railway specifications for durability and optical clarity. The limitation is the same as the consumer version. It works well above roughly 60 miles per hour, but on approach to stations, at grade crossings, during slow sections, the airflow is not sufficient to self-clear the glass, and the coating alone is not enough. Others use rotating disc wipers. A disc of treated glass, typically about 10 to 12 inches in diameter, is mounted in the center of the cab windshield and spins continuously during operation. Centrifugal force throws water off the surface regardless of vehicle speed, because the physics of the spinning disc do not depend on airflow. The disc stays clear as long as it is spinning. The limitation is that the disc only covers a small area of the overall windshield, so it is used alongside other systems rather than as a standalone replacement. Camera systems are entering this space too. Some newer high-speed platforms use forward-facing cameras with image processing for forward visibility monitoring, meaning the driver's window clarity becomes less operationally critical as long as the camera lens stays clean, which is a much smaller surface to keep clear. None of these has replaced conventional wipers across the full operational range of rail. A camera fails the same way a windshield fails if the lens gets coated with enough debris. A hydrophobic coating does not help at 10 miles an hour. A rotating disc covers a fraction of the total glass area. The humble reciprocating blade is still doing most of the work, running on compressed air, calibrated to the specific curve of a specific windshield, maintained on a long service interval in conditions that would destroy an automotive unit in weeks. The engineer sitting in that cab, watching the blade sweep back and forth, probably does not think about any of this. The wiper is just there, doing its job, powered by the same AIR that would stop the whole train in an emergency. That's exactly how rail engineering works. Solve the problem with what you already have. Make it tough enough to not need attention for a long time. And test it against everything, including the things that seem too obvious to bother testing.